Welcome. Today's video is on sections 5.7 and 5.8, inverse trig functions, both differentiation and integration. We're going to jump right in. So here are some formulas for the derivatives of arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. We're going to do some quick examples. So first example, find y prime for y equals arcsine of x plus x times the square root of 1 minus x squared. So if I'm going to do this, first thing I'm going to use is that formula for the arcsine of x, and since I don't have a formula of x, my u prime is 1, so I get 1 over the square root of 1 minus x squared. And then my second term, I'm going to use good old friend product rule. So plus 1 times 1 minus x squared plus x times 1/2, and then the inside 1 minus x squared to the negative 1/2, and then chain rule times negative 2x. All right, let's simplify this. So then I have 1 over square root of 1 minus x squared plus square root of 1 minus x squared. My 1/2 and my 2 will cancel, so I get a minus sign. Numerator is x squared, and denominator is square root of 1 minus x squared. So I have lots of square roots of 1 minus x squared. Let's see if we can combine any. I have my first term, my last term have common denominators, so I get 1 minus x squared on the numerator, square root of 1 minus x squared plus square root of 1 minus x squared. If I look at that first fraction and think about the numerator having an exponent of 1, the denominator having an exponent of 2, they're like bases. I can go ahead and subtract those exponents. And then I get 1 minus x squared to the 1/2, or square root of 1 minus x squared, plus another square root of 1 minus x squared, gives me 2 times the square root of 1 minus x squared as my final answer. Fantastic. Next example. A photographer is taking a picture of a painting hung in an art gallery. The height of the painting is 4 feet. The camera lens is 1 foot below the lower edge of the painting as shown in the figure below. How far should the camera be from the painting to maximize the angle subtended by the camera lens? So if I look at that, the angle it's talking about here is beta. I highlighted it in orange. And if I think about this right triangle, we have a couple right triangles here. I can think about opposite and adjacent sides. So my goal is to maximize beta. Okay, goal. And if I want to think about beta is not part of a right triangle, but I can make it in terms of angles that are parts of a right triangle. So beta really is theta minus alpha. And so theta is going to be that big angle for the big right triangle, and then alpha is the angle for the little right triangle. And if I have opposite and adjacent, the first thing that comes to mind is tangent. So the tangent of theta is 5 over x, and the tangent of alpha is going to be 1 over x. I don't particularly like x in the denominator because taking the derivative of that is just not going to be fun. So what I'm going to do is I'm going to go ahead and use cotangent instead. So I get cotangent of alpha is x over 5. And the cotangent of alpha is x. I think I said alpha the first time. So cotangent of theta is x over 5. Cotangent of alpha is x. So then I can find that theta is going to be the arc cotangent of x over 5. And alpha is going to be the arc cotangent of x. So now I can write a function for beta in terms of x. So beta is going to be theta minus alpha, so arc cotangent of x over 5 minus arc cotangent of x. And then I'm going to go back to those formulas and find the derivative for arc cotangent, which is negative 1 over 1 plus x squared, or negative u prime. So that's going to make a difference for my x over 5. So for the second one, it's easy. I get negative 1 over 1 plus x squared. The first one, I want the derivative of u prime. So I have 1/5 on the numerator, negative 1/5. And then my denominator is going to be 1 plus the entire thing inside squared. So x over 5 quantity squared, or x squared over 25. Actually, I'm going to write it like that first step so I don't have to do it in the next step. So now I'm going to simplify this. Don't like fractions within fractions. So I'm going to multiply the numerator and the denominator of that first fraction by 25. So I get negative 5 over 25 plus x squared plus 1 over 1 plus x squared. Let's go ahead and simplify this by finding a common denominator because our goal is to set it equal to 0. So then I get negative 5 times 1 plus x squared plus 25 plus x squared. And then my denominator is 25 plus x squared times 1 plus x squared. On the numerator, I have a negative 5 plus 25, so that gives me a 20. A negative 5x squared plus 1x squared is negative 4x squared. My denominator stays the same. And I'm going to go ahead and factor out that common factor of 4 on the numerator. So I have 5 minus x squared on the numerator, and 25 plus x squared, and 1 plus x squared on the denominator. So our goal is to maximize our function here, which after you take the derivative is the same as setting it equal to 0, right? That's where maxes occur. And a fraction equals 0 when the numerator equals 0. And the numerator is going to equal 0 when 5 minus x squared equals 0, which implies x is going to be equal to the plus or minus square root of 5. But we're thinking about x as a distance, so we don't want the negative, so we just want the positive. So x equals the square root of 5, which is approximately 2.36 feet. So that's how far I'm going to make sure my camera is from the wall. Next. Now we're going to talk about integrals, and so you'll see that here are the formulas for the integral of arcsine, arctangent, and arcsecant. And the reason why we only have these three is because if you look up ahead, up above, the formulas for the derivatives are the same except negative. So instead of talking about the negative arc cosine, instead of talking about arc cosine, it's just more convenient to talk about negative arc sine. That way we don't have to have all 6. We can just have the 3, which is fantastic. All right, so we're just going to dive in and do some examples. First one, find the integral of 1 over 2 plus 9x squared dx. And so if you want to use substitution for this one, so I'm going to look and see which one of these integrals does this resemble. And this is going to resemble my arctangent. And so my goal is to figure out what u is and what a is and all this fun stuff. Yay, so fun. So I'm going to let u equal 3x, not 9x, 3x. And so if I look at this integral, we can rewrite it as dx over square root of 2 squared plus 3x squared. And so then when I take my derivative, du dx, I get 3. So then I get that dx equals 1/3 du. So if you want to do the substitution, this is how I like to do it. If you want to do it a different way, you're totally good. So then if I go ahead and substitute this in, I get 1/3 my integral, and then du, and then my square root of 2 stays the same, plus u squared. And so now I have something that resembles the formula a little bit more closely. And so my a value is square root of 2. So in my formula now, I have 1/3 from the front, and then 1 over a, so 1 over square root of 2, and then arctangent of u over a, so u over square root of 2 plus c. And then I'm just going to go ahead and substitute back in my value for u. So I have 1 over 3 root 2, and then arctangent of 3x divided by square root of 2 plus c. Great. Our next example, find the integral of the dx over x times 4x squared minus 9. And so what I'm going to do here is I'm going to kind of ignore that x in the front for a moment and look and see, okay, which one of these is it most similar to? So I have a square root on the denominator. Oh, if I look at number 3, it's going to resemble that arcsecant most closely. So that's what I'm going to shoot for. Okay, so arcsecant. So let's see here. I am going to go ahead and write it in a form that looks a little bit more like that. So if I have dx, and then I have x times square root, and then I have 2x quantity squared minus 3 squared. That way I can see my a value better and my x value. And so a way to do this using u substitution is if I let u equal 2x, then du dx equals 2, so dx equals 1/2 du. And so then I can put this 1/2 du, and then I have here, my x didn't change, and then I have a u squared minus 3 squared. Well, this is a little wonky because I still have an x in my thing, but I can rewrite that in terms of this. So this, if I have u equals 2x, then I know x equals 1/2 u, and so I can use that to substitute back in here. So now I have my integral 1/2 du, and then 1/2 u times square root of u squared minus, u squared minus 3 squared. And then the 1/2s will cancel, which is convenient. So now I have du over u times square root of u squared minus 3 squared. So now it looks identical to the formula. So if I take the antiderivative of this using the formula, I'm going to get 1 over a, so 1/3, and then arcsecant of absolute value of u over 3 plus c. And then the absolute value of u is going to be the absolute value of 2x. So my final answer is 1/3 arcsecant of absolute value of 2x over 3 plus c. Fantastic. Part E, I think this is the last example of the day. So now we have our good old quadratic on the denominator, which does not fit any of our formulas there for antiderivatives. But if you remember, back in advanced algebra or pre-calc, you learned how to complete the square. So if I complete the square, I can make this look like something squared plus something squared. So let's do that. So if I have x squared minus 4x plus 7, and I think about x squared minus 4x, and I add or subtract something plus something, and then so if I add that same something, subtract that same something, plus 7, and I want this chunk right here to be a perfect square. So how you do that is you take your b value, and you divide it by 2, and you square it, okay? And you're going to add and subtract that. So if I take 4 divided by 2, and then square that, I get 4 again. So I'm going to say x squared minus 4x plus 4 minus 4 plus 7. So this chunk here is going to then factor to x minus 2 quantity squared, and then over here plus 3, which I can rewrite as I don't want x squared, x minus 2 quantity squared plus square root of 3 squared. Okay, so I completed the square, and then I wrote, it's like when you did quadratics in vertex form. So then I wrote the 3 as square root of 3 squared, so I can see it's also square. So now I can rewrite my integral as dx over x minus 2 quantity squared plus square root of 3 squared. And so my u is going to be x minus 2, and my a value is going to be square root of 3, which is helpful because the derivative of x minus 2 is 1. So don't have to worry about substitution and possible factors being in the front of my answer here. So my answer then, if I look at my antiderivatives, this one matches arctangent. So I have 1 over a, so 1 over square root of 3, times arctangent of u, so x minus 2 over 3, square root of 3, plus c is my answer. And we are done. That is all the examples for today. So go ahead